Hi everyone, I'm back again. I'm here to do Leetcode problem number 78 subsets. Let's read the problem. Given an integer array nums of unique elements, return all possible subsets. The power set. The solution set must not contain duplicate subsets. Return the solution in any order. Take a look at this. A subset of an array is a selection of elements, possibly none of the array. Okay, notice that we're given 1, 2, 3, and we return the empty set 1, 2, 3, 1, 2, 1, 3, 2, 3, and 1, 2, 3. Notice that 1 and 2 is a subset, but 2 and 1 could also be a subset, right? 2 and 1, but it sure looks like that. 2 and 1 and 1 and 2, they basically count as just one subset. So the ordering doesn't really matter as long as you grab the subset itself. 1 and 2, 2 and 3, they count as one, right? And if it's 0, then you return the empty set and the subset with 0. Which makes sense because whenever you have the input, the empty set is a subset as well as the set itself is a subset. Let's take a look at the constraints. So we have one is less than or equal to nums.length, which is less than or equal to 10. That's good. So we know that the input array is not that large. We also know that the values themselves in the input array is anything from negative 10 to 10, which is good, a pretty small range. And we know that all the numbers are unique. Okay? This is, of course, a backtracking problem. But let's take a look at the topics. This is an This is an array. Backtracking or bit manipulation problem. Let's take a look at the approach. Basically, backtracking is a brute force solution where you're going down. You're basically doing a brute force solution, which is actually the optimal solution, where you're basically going through the inputs and basically finding all the subsets in a very brute force manner. You're going to be doing recursion as you go down. It's basically going to form like a tree. It's going to be form like a tree where you're going to be doing breadth first search. You're going deep down the paths, and then after you find a valid subset, the backtrack is going to go up the tree, and then you may add like a new value to initiate a new path along the backtracking to see if you can get another valid subset. That's essentially how it works. It's kind of hard to explain it. It's easier if you visualize it, but essentially this is a depth first search problem, and which if you think about it, that is what backtracking is. And so let's start doing it. So define a res and cur list that will hold the results and the current subset being processed. Return res. Then what we're going to do is So first let's set up the skeleton, right? So we're going to do res equals a list as well as cur equals a list. And then we're going to return res. That's the skeleton, basically. The results in the current subset that's being processed, and then we're going to return the results, right? We are going, and here's where we really get started. We're going to need the help of a helper function backtrack. All right, so let's do that. Def backtrack start, and then we call this function with 0, starting with index 0. Okay, so now this is basically the skeleton, right? We're gonna have to do backtracking, and basically whenever you do backtracking, you basically always need some auxiliary function to actually do the backtracking operation. You have some kind of holder that will process the current thing that you're processing, as well as another holder that will hold the results after the current one has been processed and can be added to the result, right? So this is what we're gonna do, in the sense that inside backtrack, this is what we're gonna do. We are going to add a copy of cur to res, right? We want to, whenever we call the backtrack function, we know that the processing of the subset is done in the second half of the function. So whenever you call the recursive step, you know that once you reach the top of the function, you have a current subset that's been processed, so we can add it to the results. Then what we're going to do is a loop from start to length of nums, which makes a lot of sense. If we want to start finding some of these subsets, we're going to have to start trying out different combinations of things, right? So we're going to have to start with the first one and see how many subsets we get, and then after all the paths that start with 1, such as 1, 1, 2, 1, 3, 1, 2, 3, after all these ones have been explored, well, maybe we need to explore 2, right? We also need to explore 2 and possibly even 3. So loop from start to nums, and this is where it gets kind of tricky. If the current value with index I, the current value with index I is not in cur, add it. Call backtrack with I plus 1, and then after the backtrack operation, pop, then you pop the last value from cur so that you can explore other paths along, so you can explore other paths that may result in a subset. You let the backtrack function find them. So essentially what you're doing inside the backtrack function is you're gonna, I explained this, you're looping from start to length of the nums, right? You got to start starting with the first value, you got to pick it and start exploring some of these combinations to see if they form subsets. Then what you need to do is you need to see if the current value with index I is not in cur, add it, right? This condition right here makes it such that 1 and 2 and 2 and 1 are basically counted the same. You call backtrack after you're done with this value, you call backtrack on the next value, and then after you explore a particular path, such as let's say 1 and 2, well, 1 and 2 resulted in 1, 2, and 3, right? You have to pop up the last value. You already explored 1 and 2, you pop up the last value, and then that gives you the ability to get back to 1, and then you can add 1 to the subset, add 3 to the subset, and start exploring some combinations of 1 and 3. It's very hard to explain unless you visualize and draw it out, but let me just do it. Res.append cur, a copy of cur for I in range start to length of nums. You do if, well, you can actually do this, val equals nums I. If val not in cur, then what do? Cur dot add append val. Then you do backtrack I plus 1, and also you do cur dot pop. And I believe this should be a working solution. There we go. All right, and so the TC is n times 2 to the n, and the SC is also, whoops, sorry, the same thing. The time complexity is n times 2 to the n because every time we do a backtrack operate, we not a backtrack, every time we have a split, if you take a look at the subsets, we can either for each of the values in the nums, we can either include it or we won't include it. We can either include it or we won't include it, but we have to explore both paths. So that's 2, and there's n values in here, so it's 2 to the n. It's 2 times 2 times 2, which is 2 to the n. And then you have n values, right? You have 2 right here, 2 right here, 2 right here. That's 2 to the n times n. And the space complexity is also n times 2 to the n. Let me make sure I get this right. 2 to the third is, let me make sure I get this right. N times 2 to the n. Yeah, it's right. So let me try explaining that one more time. So each time you have a choice, that's it. Either you include this one or you don't include this one. So there's two choices here, 2 choices here. That's 2 to the n, right? That's 2 to the n, and then you have n values that you're going. So that's n times 2 to the n for time complexity, and that's the same space complexity. This is a relatively easier backtracking problem, but I've always had problems with backtracking, so it's been a good practice. I was able to solve it, and there is no other algorithm that's better than this one. For this problem, you have to do the brute force approach, and I did it. So thank you very much, and I'll see you at the next one.